So chapter 3 was called A World of Particles, and we were introduced to the atom and the particles that make up every single atom. We started by looking at a brief overview of the history of atomic structure and models of the atom. Remember that a model is a simplistic representation for something that's more complex, and you're really not responsible for any particular model, who made it, when it was made, anything like that. But you should understand that the model of the atom is progressive. It changed over time, became more complex. If we look at what happened, we started with Dalton, who had a very simple solid sphere model. Thomson did the cathode ray experiment to discover electrons. That was the first particle discovered. Rutherford did the gold foil experiment to discover the nucleus, which was positive and dense and small in the center. Bohr had electrons that were orbiting the atom, and then Schrödinger came up with the quantum model that we have now, which is very similar to the planetary model, but the electrons, he said, and we know now, are not orbiting the nucleus, but they're found in regions of probability around the nucleus, spaces around the nucleus where an electron most likely will be found. The atom is made up of 3 subatomic particles: protons, neutrons, and electrons. You should be familiar with the charge for each one, the mass in atomic mass units for each one, and their location. Even though we have the quantum model as our most current and most accurate, we still use a model similar to Bohr's as the simple atomic model to represent an atom, because it's just simpler for us to draw, where the protons and neutrons are in the nucleus and the electrons are on the outside. This simple atomic model is representing this specific isotope, and we're going to get to review those in a minute. If I count the number of protons and neutrons here, there's 6 protons. That's identifying the atomic number, which I could look on the periodic table, and that tells me that it's carbon. 6 neutrons tells me that the atomic mass is 12 AMU, because each proton has a mass of 1 AMU. Each neutron has a mass of 1 AMU. So 6 AMU plus 6 AMU gets me 12 AMU, and that's the atomic mass of that specific individual atom. The electrons have no mass, so we don't worry about them. Isotopes are atoms of the same element that have the same number of protons but different numbers of neutrons. Therefore, their masses are different. We can notate isotopes in a couple of different ways. The first two are, well, the first one's really a shorthand. The second one is really the name of the isotope, how we would say the name of an isotope: carbon 12, carbon 13, carbon 14. The 2 symbols down here are representing the mass number in the upper right-hand corner and the atomic number in the lower left, and the last one here is just referencing the mass number, because we don't really need to write the atomic number down, because we already have the element, and we can find the atomic number on the periodic table. The basic notation for an isotope, which we call isotopic notation or an isotope symbol, will have the symbol of the element as represented by X here, the mass number, which is represented by A, which is the number of protons plus the number of neutrons, and then the atomic number, which is just the number of protons. So using that information, we can actually calculate the number of neutrons for a specific isotope. Here is silicon-28, silicon-29, silicon-30. They all have 14 protons because, well, they're all silicon. They're all the same element. They all have the same number of electrons because, remember, for an atom, atoms by definition are neutral, same number of positive and negative charges. The number of neutrons we get by taking the mass number and subtracting out the number of protons, that will get me how many neutrons are left. So silicon-28 has 14 neutrons, silicon-29 has 15 neutrons, and silicon-30 has 16. In the symbol on the periodic table, we should be familiar with the element symbol, obviously. The whole number on the periodic table is the atomic number, telling me the number of protons there are in each atom of that element. And the decimal here is the average atomic mass. Different than the atomic mass up here, right? The atomic mass is just the mass for one individual specific isotope of an atom. The average atomic mass is the weighted average of all of the isotopes. And that's what we're gonna look at now. Average atomic mass is the weighted average of all naturally occurring isotopes of an element. The average atomic mass will be closer to the isotope that is present in a greater abundance. So for example, I gave you two isotopes of carbon, the ones that exist the most in greatest abundance. Carbon-12, which has a mass of 12 AMU each, exists 99% abundance, which means in nature, of all of the carbon that exists, 99% of the atoms will be carbon-12, meaning you're more likely to find a carbon-12 atom. Then a carbon-13, which each have a mass of 13 AMU, it's only 1% abundant, meaning of all the carbon atoms, only 1% exist as carbon-13. Now, the easiest way to look at it would be to assume that you had a sample of 100 atoms, like here. The percent abundance means if we assume we had 100 atoms of carbon, 99% of them, aka 99 atoms, would be carbon-12, and 1% or one atom would be carbon-13. So you can imagine if we took an average mass of this sample, the average mass of the atom is going to be closer to that of carbon-12 because there's more of it. So when we calculate it, we do just what I said. We're going to assume that we have 100 atoms. And if we do, that means 99 of the 100 atoms are going to be carbon-12 with a mass of 12 AMU, and one atom is going to have a mass of 13 AMU. That will give me the total mass of all 100 atoms, and then I want to divide by 100 to get my weighted average, and we get 12.01 AMU. Check the periodic table. It matches out. It makes sense because most of the atoms are carbon-12, so this number should be close to carbon-12. I want you to pause the video now and try calculating the average atomic mass for magnesium given those three isotopes, and when you're done, you can resume it and check your work. So if I'm assuming 100 atoms again, 78.99 of them will be magnesium-24 with a mass of 24 AMU. 10 of them will be magnesium-25 with a mass of 25 AMU. And 11 of them will be magnesium-26, mass of 26 AMU. Again, that will get me the total mass of all 100 atoms. I'm going to divide by 100 to get the average atomic mass, which is 24.3 AMU. Does it make sense? Sure, because most of my atoms are magnesium-24, so the mass is going to be closer to 24. Some other problems we looked at that we can answer. Predict the two most abundant isotopes of silver, if we're given this information about silver on the periodic table. I see the average atomic mass is 107.866, so my two most abundant isotopes are going to be silver 107 and silver 108, because averaging those together will get me somewhere in between that that number. And the one that's most abundant is going to be the isotope that this number is closer to, which is silver 108. So we should expect to find more silver 108 than silver 107. How many protons, neutrons, and electrons would each isotope have? Well, they're both silver, so they both should have 47 protons, as indicated by the atomic number. They both are atoms, which means they're neutral, so they both should have 47 electrons. The neutrons are going to come from taking the mass number and subtracting out the number of protons. So we should get 60 neutrons for silver 107 and 61 neutrons for silver 108. The last little bit we talked about in this chapter was actually a large portion of it was nuclear chemistry. And we started off with looking at nuclear stability, the idea that some isotopes are stable and other isotopes are unstable, and that has to do with the ratio of protons to neutrons in the nucleus. If the ratio of protons to neutrons is not correct for a certain atom, the nucleus is unstable, and it's going to do something to become more stable. And that something is going to be, it's going to decay. It's going to give off a radioactive particle to change the nucleus in some way to become more stable. We looked at a naturally occurring isotope chart, and I gave you a snippet of it here, that gives us, it plots the number of protons and neutrons, so we can actually look at the different isotopes that exist naturally for some of the elements. And of the naturally occurring isotopes, we can see which one's the most abundant, which one is radioactive, right? Like carbon-14 is radioactive, or it's unstable. And that led us into a discussion about the terms natural versus stable, that they don't actually mean the same thing. Natural means that it's found in nature, that it's not man-made in the lab. Stable means that it's not radioactive or undergoing radioactive decay. So we have to be careful of those two terms. We looked at elements after atomic number 82 are going to be the ones that don't have any stable isotopes at all. Elements after atomic number 92 are all man-made in the lab. They don't exist naturally. The nuclear reactions that are responsible for helping these nuclei become more stable, we looked at three specifically. They were alpha decay, beta decay, and gamma decay. So you can read those definitions. You should be familiar with what that means, and most importantly, be familiar with the symbols for alpha, beta, and gamma, and what they do in terms of a nuclear equation or reaction. That if something's undergoing alpha decay, the atomic number is going to decrease by 2, and the atomic mass, or the mass number, excuse me, is going to decrease by 4, because you're releasing 2 protons. That's why the atomic number is going to decrease by 2. But in addition to 2 protons, you're releasing 2 neutrons, and that has a mass of 4, so that's why you're decreasing your mass number by 4. Beta decay actually increases the atomic number by 1. Mass stays the same. And remember, beta decay was a little tricky because basically what's happening in the nucleus is that you're converting a proton, or you're converting a neutron into a proton. So you're gaining 1 proton, you're losing a neutron, so that's why the atomic number increases by 1, because you're adding 1 proton. But the mass number doesn't change because when you change that neutron into a proton, they both have the same mass, so there's no net loss or net gain of mass anywhere. Gamma decay has 0 charge and 0 mass, so you're not changing the atomic number, nor are you changing the mass. I'm going to add the negative sign to that beta there. Now, we looked at filling in reactions for alpha decay and beta decay. So we'll review that, and then I'm going to let you try a couple of on your own if you pause the video. For the first example here, we have tungsten 184 that's undergoing alpha decay, and I realize that because of the alpha particle that's on this side of the arrow. It's releasing an alpha particle. Remember that these numbers on one side have to add up to the numbers on the other, and the alpha decay is going to cause the atomic number to decrease by 2. So this changes to 72, and it's going to cause the mass number to decrease by 4, so that's going to change to 180. And then the last thing I have to do is fill in what isotope did this change into now. Remember, nuclear chem is the only type of reaction where the element can actually change. And it does change because I'm changing the number of protons. How do I find what element 72 is? I look on the periodic table, I find out that it's hafnium. Carbon-14 here is undergoing beta decay, as indicated by the beta particle. Beta decay is going to increase the atomic number by 1. And I can just cross-check that because 7 minus 1 gets me 6, and that equals 6 on the other side. The mass stays the same. That's the element nitrogen, so carbon-14 is undergoing beta decay to change into nitrogen-14. What I'm going to ask you to do is pause the video and fill in the rest of the nuclear reactions here, and then unpause the video when you've completed them so that you can check your answers. Now for this, lead-210 is undergoing some sort of decay to change into mercury-206. They gave me what the new isotope is. This time I'm figuring out what the particle is, and if I look at the missing numbers, it's an alpha particle. Here, sulfur-35 is turning into chlorine-35, again by undergoing some sort of decay, and if I look at the numbers, that makes sense. That's a beta particle. Or I could have also written the beta particle like that. Here, something is undergoing alpha decay to turn into thallium-207. What is that something? Well, 81 plus 2 is going to be 83. 207 plus 4 is going to be 211. That's bismuth, and that makes sense because if bismuth is going to undergo alpha decay, it's going to decrease its atomic number by 2 and decrease the mass number by 4. Something's undergoing beta decay to turn into nickel-60. Top number is 60. Bottom number is 27. And that something is cobalt, if we look in the periodic table. The last two here, you're writing out the entire reaction. So calcium-45 is undergoing beta decay to turn into what? Increase the atomic number by 1. Mass number stays the same. What element is number 21? That is scandium. Plutonium-234 is undergoing alpha decay to turn into something. That something is uranium-230. And those are how you complete those. Last type of reactions we looked at were nuclear fission and fusion. You should know the general differences between the two. The idea that fission is taking a larger, heavier nucleus and splitting it into several lighter, smaller nuclei. Fusion is taking several smaller, lighter nuclei and fusing them together into one heavier, larger nucleus. Fission occurs in nuclear reactors. That's what powers many cities and states across the U.S. and across the country. And then fusion happens in the sun. And fusion is what was responsible for all of the elements that were first made when the universe was created in the Big Bang. Our sun is fusing hydrogen into helium, and then helium into carbon, and carbon into oxygen. It just keeps going down the chain as it keeps fusing lighter elements together. And we said that iron was the last element. It was sort of the last stop in the fusion chain there because it's not energetically favorable for a star like the sun to fuse anything heavier than iron because it starts to lose energy after that. But there are other processes out there in the universe that will fuse heavier and heavier elements. You should be able to recognize whether a reaction is fission or fusion. This I recognize as fission because I have one thing on this side splitting up into two, and as long as that's not an alpha or beta particle, if it's another nucleus, then it would be considered fission. How do we test that? Well, again, I'm just keeping the numbers the same on either side. If this is 91, 77 plus whatever this number is has to get me 91, and that's 14, and the same thing with the mass numbers up top. That'll be 39. I look on the periodic table. This is silicon. So I understand that this is fission. I have this palladium-231 splitting into iridium and silicon. Iridium-191 and silicon-39. For the fusion, I'm fusing these two things together. So 2 plus 1 gets me 3. 4 plus 2 gets me 6. Atomic number 3 is lithium. What you can do is pause the video now. Try the two equations that are below, and then you can turn the video back on to check your work. That's bromine 103 and neon 21. The very last thing that we looked at in this chapter was, can gold be made via nuclear reactions? Because nuclear reactions and nuclear chemistry is the only time we saw where you can actually change one element into another. In chapters 1 and 2, we were looking at a lot of chemical reactions, especially in chapter 2 with the copper cycle, where we tried to change the copper through a chemical reaction, but understood that because of conservation of mass, the copper was always there in some way, shape, or form. But nuclear reactions have the potential to change, and we see it all throughout here, change what the actual atom is by changing the number of protons. So we looked at all 4 different nuclear reactions we looked at and said, is it possible for any of them to help us create gold? And we looked at alpha decay. And we worked backwards, and we said, what element what isotope can undergo alpha decay to give us gold, right? To give us an isotope of gold. And we found out what it was, but then we looked on that isotope chart and we found out that isotope that would undergo alpha decay to give us gold does not exist. So alpha decay was out of the question. We did the same thing with beta decay. What isotope can undergo beta decay to help us form gold? We found out what that isotope was, but again we looked on the isotope chart and that isotope is non-existent. We looked at fission. What's one nucleus that can split up into 2 or 3 or 4 smaller nuclei that could possibly give me gold as one of those smaller nuclei? And we talked about how fission is sort of random. When we split apart a nucleus, it splits in several different possible ways, so getting gold from that type of nuclear reaction is not feasible because you would never know which time is going to get you gold, and if you did get it, you weren't going to get that much of it. Fusion was our last hope, and we came up to the ultimate conclusion that, yes, we can make gold via a nuclear reaction. Fusion would be that reaction, but the problem is it only occurs in outer space in the stars. And most of the gold that's here now is the gold that's going to stay because that was formed from the Big Bang when the universe first started. The gold that's being made now in stars is very small and it's floating somewhere out in outer space. It's definitely not here on Earth. And to get fusion to be done here safely on Earth is not feasible. There's large costs, there's large amounts of energy, and it's just not safe for us to do it on Earth. So the ultimate answer to the question is both yes and no, with us leaning more towards no in terms of doing it here on Earth. Yes, fusion is happening out in the universe and it's forming gold all the time, but in terms of doing it here on Earth, the answer is no. And that's where we wrap up this chapter with A World of Particles.